So, what we did was, in this activity, was just apply everything that we saw in lecture last time. And so lecture just seemed, oh, that was easy, right? And so, oh. And so, when you look at this, there's context, quite a bit of context in what we're looking at. And so, this is the kind of application I would like for you to be at level, okay, in using this. What's going to be very, very important is knowing the amino acid structures and what group they reside in. Okay, are they hydrophobic? Are they polar? Are they charged? Which charge are they? Negative or positive? Because this is going to influence a lot of the interactions that we see. All right, I'm going to then want you to understand that the pKa's and the pH's are important because, yes, glutamate is a negatively charged amino acid, normally. Now, what is normal in the body? When I say normally it's negatively charged, what is my assumption? pKa's
neutral pH.
At which pH?
Neutral, 7.45.
About 7-ish, yes. A little over 7. The pKa never changes, but the pH of the solution can. Okay. And so normally it is a negatively charged amino acid. But under certain pHs, it will be neutral, protonated and neutral. That changes its behavior quite a bit. And so when we look at protonation states, there are two protonation states. You have the protonation state of the amines, and you have protonation state of the oxygens. And so if I add just a slide here, and what I want to do is, if you have a nitrogen, okay, if you have a nitrogen, its normal state is this. This is the deprotonated. When it becomes protonated, is positively charged. On the other hand, if we have an acid, which is the most often one we see, and we look at it, the protonated versus the deprotonated state, the deprotonated state is negatively charged, while the acid that's in the protonated state is neutral. And so protonated state and deprotonated state doesn't mean I have charge or not. It really depends upon what you're looking at. Okay? If by chance you were looking at a thiol, the protonated state, let me go back. Thiol would be in the deprotonated state negative, and the protonated state neutral. So each one has its own context about what its charge might be depending upon what's happening. And what you would have to do is look up the pKa for everything to know that. On the exam, I would give you a list of those. This is not the things that you would have to memorize. What do you have to memorize? The pKa's. Which groups? Normal protein. What are the N-terminus values for every amino acid? Somewhere between what? 9 and 10. And what about the C-terminuses? Between 2 and 3. And we default pH at 7.4-ish. That's the only thing that I would want you to memorize, but I don't want you individually memorizing each amino acid. The R groups, we will give those to you in a assignment or on the exam. Okay, that's too much information to memorize. Nobody memorizes those. Okay. Oops. All right. I put that in the wrong spot. Remember the fact that we do have a peptide bond that has a double bond character means that there is not the freedom of rotation around the carbon of the acid and the nitrogen of the amine. It is actually double bonded in character. We said that this gives two possible angles, a phi and a psi angle, that are possible, meaning that there's just a twist that can happen, and we can measure that twist. All right. Now, a plot of these possible available angles is called a Ramachandran plot. Okay, and these are the phi and psi angles. What's in front and behind the alpha carbon, or the carbon that has the R group on it. Here's an example of what a Ramachandran plot would look like. Not all combinations of angles are available. And so we highlight and make darker the angles that are most often seen. And when you look at that, these angles will represent certain types of folds that we see in proteins. And so they fall into certain categories. Now, some are even more limited. The larger the R group, the less freedom of movement you have. And so this is a generalized presentation of what the angles are available. Glycine would be the most free because it has a little tiny R group of a hydrogen. Tryptophan would be the least because it has a very large double ring. But not all angles are available. And so there are limitations in terms of how the peptide can fold, which is good if we want to model something. The more constraints, the better the computer can make a guess at things. The less constraints, the more random it could become, and the calculations become more complex. Okay. Now, here's the problem with the phi and psi angles and trying to predict what might happen. We have lots of different types of structure that it can be. I introduced these. We'll actually show them in just a moment. But let's say structure 1, 2, and 3. Okay, I say alpha helix, beta sheet, and beta turn. Okay, there are 3 different kinds of structures that it can be. There's a probability for each amino acid to be in one of those particular structures. And you can see a bar graph that shows what is the probability of it being in one or the other structure. Now, at the top, we order it by structure 1, alpha helix. The what is that? GLU? Glutamate, not glutamine, tends to be in an alpha helix a lot more often than not. But is it exclusively alpha helix? No. It can be in the other 2, and it can be significantly in some of the other 2. And if you go all the way down to the bottom, glycine has the ability to be an alpha helix. It's the least likely. It's the most likely to be in the 3rd conformation, beta turn, but it can be in all of them. And so there is not a 100% predictor. There is a probability. And when you start moving all of these together, even if you know what the primary sequence is, there is so much variability in it that we tend to have a problem to, in a computer, estimate what the folds will be or what the angles will be, because they can be all over the place. Okay? And so we have to do some other things. But predictions about how proteins fold, just based upon the linear sequence, the primary sequence, the lowest level of information, is very hard to, if not impossible, to do by itself. You have to have other experimental evidence to help support the idea of coming up with what the structure is. Okay, now, one thing. If I want to predict the structure, okay, I might get a 60% at the best guess. All right? So if you went into a test and you're going to get a 60%, feel comfortable about that? Oh, it sounds like a GChem 2 exam, right? Okay. You feel like you know it all, but oh my goodness. Right? And that's based upon even 6 amino acids. Okay. Now, when we actually look about predicting structure, okay, the types of structure that we're going to look at are secondary structures first, and then tertiary structure, the overall fold. There are methods that we use to measure these, and we'll show you a couple of these. Okay, and so we'll introduce a couple of secondary structures and then talk about tertiary. Yeah.
How important is it for us to understand the left-handed versus right-handed?
The left-handed versus right-handed. this is what you need to know. One exists and one doesn't, and normally. And the left-handed, even though that it is technically possible, and we can actually force it in the laboratory, we don't see that in our amino acids in real proteins. So that's kind of an oddball thing. We can force it into that way, but it just isn't seen naturally. The alpha helix, one of the most typical secondary structures. And remember, secondary structure is the relationship of amino acids relatively close to each other. Okay? So how does an amino acid number 1 and the fourth one away from it relate to each other? The second one and the third one and the fourth one away. What happens is the amino acids create a curl. You know, a rod that is a helix. That's wonderful. Use the name to describe what it is. Okay, and it twists around each other. It's very stable. Okay, and we represent it in different ways. You can actually talk about the backbone. So the nitrogen, the alpha carbon, the carbon of the acid, the nitrogen of the next amino acid, and that's what that first structure is. It's the carbon-nitrogen connection, and you can actually see it wrapping around, okay, twisting up. But what we like to do is to use a ribbon structure, and you can see that twisting much better in the ribbon structure. It's easy to see. But here's the problem when you see alpha helix. That is just the backbone. Remember, you have all these R groups, right? That's where the important piece of the puzzle comes in terms of functionality. So I'm going around and wrapping around a ribbon there, but jutting out are all these side chains, all the R groups. Now, here is that same, all right, the alpha helix, if we actually look at it, if you look at residue in, the carbonyl will make a hydrogen bond with 3 residues away. Okay, and that 3 residue away, the nitrogen and the carbonyl will make a good hydrogen bond. It's the right distance, and so, but as it curls up, you get hydrogen bond followed by hydrogen bond followed by hydrogen bond followed by hydrogen bond. And so this rod-like structure becomes very rigid because of all of that hydrogen bond nature. And so there are 3.6 residues per turn in a normal hydrogen bonded alpha helix. And the protein is right-handed or clockwise. This will lead us to a spectroscopy analysis. We never see the left-handed in natural form. We can force it under really odd conditions.
Is there any benefit to?
No, there's not necessarily a benefit. It is just like handedness in our amino acids. We only see the L, we don't see the D. Not necessarily is it important. We could have both of them, and viruses do have both versions. It's just something that we see. We now know for amino acids, it's the enzymes that force everything to be synthesized as L. But you can see it's still available even sterically. It's fine. It just we don't see it. The beta sheet is a little bit different. It is still held together by hydrogen bonds. Okay, and the amino acids of the peptides will lay against each other. Now there are 2 versions: anti-parallel and parallel. What is the difference? Other than antis in front of one another.
The N-terminus and C-terminus are all.
It's the directionality. Okay? In the anti-parallel, if you look at one ribbon, the N-terminus is up. The next one, the C-terminus is up. The next one, the N-terminus is up. So what has to happen is the peptide has to start here, and then somehow has to turn around, and then come this way. And then somehow has to turn around and come that way, so that this grouping can bind together. Now, the bonds are, again, nitrogen to carbonyl to hold the structure together, and I get this pleated sheet. Okay, this sheet of structure. Now, what's important about the sheet structure? The R groups. What happens is there are R groups that are sticking up directly towards you, and there are groups that are directly behind. It's interesting because you could have a sequence where all of the ones on this side are positive. So this base is positively charged. And then on the other side, all the ones sticking on the bottom might be hydrophobic. And I can have very, very different signs. The parallel, meaning that the directionality is all the same way. Which of the two is stronger in terms of how it is held together? Anti-parallel. Why?
Because the R groups are able to be separated from charges.
Not the R groups, because the R groups were both there, either up or down. So the R groups are up or down, but the parallel does have a little bit more stability than the anti-parallel has a little bit more stability than the parallel. Yes?
Is it because the anti-parallel is built in a way that you can make the hydrogen bonds closer?
The hydrogen bonds are direct overlaps, and every bonding that we have, direct is much better. The parallel are on angles, and so it makes it a little bit less energetically favorable.